Where we left off, we were talking about electron configuration. Remember, writing electron configuration, really two things that are really important to remember, and that is basically how many electrons maximum you could put into the different orbitals. S could hold 2, P subshell could hold 6, D subshell could hold 10, and F subshell could hold 14. You can recreate the order pretty simply, as we talked about. S's begin on the first energy level, not until the second energy level that P's start, not to the third energy level that D start, and really not to the fourth energy level that F start. So basically, if you just remember that sort of order, all you have to do really is just fill in the numbers underneath each of these. And I did it again. That is S. Put the right letters would be good. 4S, 5S. 6S and 7S, and obviously here this would be 3P, 4P, 5P, 6P, 7P, 3D, 4D, 5D, 6D, and 5F. And really quickly, you could again recreate the order that you need to write the electron configuration there on the page. We talked about, I think at the very end, again, sort of a shorthand that you could do with electron configuration, and that involves noble gas configuration. So for example, we have something like sodium, which is 11, that is 1s2, 2s2, 2p6, 3s1. When we look at something like sodium, if we take this part of the configuration, that is 10 electrons, which is basically neon's configuration. So you could go neon and then continue on with the rest of the electron configuration. And you could do that pretty much for any electron configuration. It does have to be a noble gas group 8 there. That does need to go in the parentheses or brackets, and then you just continue on with the electron configuration. Any questions on that there? Now, when we look at, I got here coming maybe, there we go. When we look at the periodic table, you could actually sort of count off electron configuration from the periodic table. And the first two groups on the periodic table are what are referred to as the S block. And the S block has 2 electrons. So that's why it's group 1 and 2, which would be the 2 electrons. Group 3 through 8 is what is referred to as the P block. And that is 1, 2, 3, 4, 5, 6 electrons as you go across it. D block is the transition metals, and that is 10 electrons. So if you count all the way across there, that is 10. And over here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. The 2 rows on the bottom are the F block. So you can count electron configuration off of the periodic table by doing so. I don't know if it's the best idea per se, but you definitely can do it. So for example, you know, wish I had to have a better, just scoot through here real quick. Do I have another? Let's see if I have a periodic table. There we go. Maybe. No. Okay. So, you know, if we were to do it, there's also obviously period numbers 1, 2, 3, 4, 5, 6, and 7. And we do use the period numbers as like the principal quantum number, the energy number. So, you know, if we were doing sodium, which is like right here in this spot, we would go starting up here. This would be hydrogen, all the way to helium would be 1s2. Coming through here, lithium and so forth to this spot would be our 2s2. This is now period 2, and this is our P6, so 2p6 down to neon, which is right here. And then going one more over, this would be 3s1. And again, you could kind of count off the electron configuration from the periodic table. There are a couple places where you do have to be really careful. And right here, this guy is our first transition metal. Thank you. And Transition metals, though, are the Ds, and they do start on the 3rd energy level. So even though that is on period number 3, that is actually 3D1 would be that first space there. It is 1 behind the period number, so that's an important thing if you're going to try to count it off the periodic table to watch out for. Also, if you remember, these 2 rows down here technically go like right here, on period 6 and 7. These are the Fs. So this very first guy down here is actually 4F1, and that is actually 2 behind the period number here. So there's a couple places where you got to be really careful if you want to try to count off the electron configuration from the periodic table. It's a good way maybe to check yourself. But again, get into that transition metal region, stuff like that, there are some places where you can go wrong if you don't count it correctly. Now, if you use our zigzag, you'll never kind of screw up that back and forth thing. You should always sort of end up with the right electron configuration. Any questions on that there? Okay. So we sort of talked about this just a second ago at the end. Again, if we looked at something like potassium, which is 19, if we wrote out the electron configuration, it would be this whole thing. But again, if we just took the electron configuration from this point, that is 18. And again, our noble gas, which corresponds to that, is argon, which would go in brackets. And then we would continue on with 4s1 to give us that sort of noble gas. So always got to be the noble gas that comes right before whatever element you are writing the electron configuration for in order to do that correctly. Any questions on that there? Now, a couple of things here. There are a couple of exceptions. I don't remember if we talked about it or not, but there are some exceptions to the normal electron configuration. And the 2 notable ones that you should remember is chromium, which is number 24, and also copper, which is 29. So if you follow the zigzag thing that we just made there with the arrows like we've been doing, you would write the electron configuration as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. And the exception with chromium happens right here. What ends up happening is it's just been found experimentally to be a lot more stable with an extra electron up in the d orbital, 1 less electron in the s orbital. So the correct sort of configuration for chromium should be 1s2, 2s2, 2p6, 3s2, 3p6, actually 4s1, 3d5. So that is actually one exception to sort of normal electron configuration that we come across a lot. Copper is pretty much similar. Copper is argon, 4s1, 3d10. It actually has 1 more electron up there in the d orbital. It's really the same exception, except that if you sort of wrote it for copper at the end, it would be 4s2, 3d9. It has that extra electron up there in that d. They're able to do that because, as we talked about, the 4s orbitals and actually the 3d orbitals are really, really close in energy. When the electrons go in, they're super close. So it doesn't take a lot for that extra electron to sort of find its way up here and be promoted. And it also does a couple of things. It creates, for example, for chromium, maximum parallel spin. So we created like an electron in each of the d orbitals. We also pair up the d orbitals there for our copper. And those are 2 exceptions to the normal electron configuration that you should be aware of. If you look where copper is on the periodic table and chromium, and you go below and kind of over to the left there from copper, there's a lot of ones that actually do have a lot of exceptions in that area. For example, PD has like no electrons in this 5s. It's like totally empty. They've all gone up to the D. Silver is another exception that's underneath there. But for us, you just need to worry about these 2, which is chromium and copper. Any questions on that? Now, what actually happens, speaking of sort of the 4s and 3d orbitals, is actually when the electrons go in, the 4s is lower in energy, which is why they do get the electrons first. Once we start actually putting electrons into the d orbitals, there's actually a switch in energy that occurs, and actually the 4s becomes higher in energy, and the 3d actually becomes lower in energy in this particular case. So there's actually this switch in energy that occurs once we start filling the d orbitals with electrons. And that's why sometimes you may even see electron configuration written where it looks like all the threes are in order, or go like 3s2, 3p6, 3d5, 4s2, or something like that. And the reason for that is it's actually written in terms of energy, which is actually what occurs after the electrons go in. But for our class and most chemistry classes that you use, we usually write the electron configuration based on filling order, which is that zigzag thing that we did. And that is how you should write the electron configuration. But occasionally, every so often, you'll see it kind of written almost in order. And that's really based on energy rather than actual filling order. Any questions on that there? Now, let's say we had something like chlorine. And chlorine will gain a -1 charge. What happens when things gain a charge? So chlorine is 17 electrons with no charge, which means its electron configuration 1s2, 2s2, 2p6, 3s2, 3p5. When it gains a negative charge, did it gain or lose electrons? Did gain. So something with a negative charge like chlorine would have 18 electrons, which means you do need to adjust the electron configuration, 1s2, 2s2, 2p6, 3s2, and 3p6 would actually be the electron configuration for chloride that has a -1 charge. Now, if we look at, say, something like calcium, which is 20, it has 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 as its electron configuration. When calcium gains a charge, it actually gains a +2 charge, which means it has now lost 2 electrons. It ends up with 18 electrons, which means its configuration for calcium with a +2 charge, 1s2, 2s2, 2p6, 3s2, 3p6. 18 electrons on the periodic table are who? It is argon. Yeah, it has 18. So what ends up happening here is chloride, for example, with a -1 charge, calcium ion with a +2 charge, and argon, they all have the exact same electron configuration. That is what is known as being isoelectronic with each other. Isoelectronic means that there are multiple things that have the exact same electron configuration. So this is actually a very important idea and concept here, and what we'll talk about here when we get into bonding. But the idea of all bonding is basically for everybody to achieve the same electron configuration as the noble gases. So how metals do it is they typically will lose electrons and back up to the noble gas that comes right before them. So if you look on the periodic table where calcium is, 2 back is argon, which is the noble gas that comes right before it. And nonmetals typically will gain electrons and go forward to the next noble gas. So again, if you look at the periodic table and find chlorine, one more spot ahead of chlorine is argon, and it moves itself into the same electron configuration as a noble gas. That's really the basis of all bonding, is basically for everybody to achieve really the same electron configuration as noble gases. It is the most stable sort of configuration, right? Noble gases are chemically inert. They are very, very stable just by themselves. They don't need to react with people. And that's really the goal of what everybody's trying to achieve through bonding. And the way they do that is to gain and lose electrons, especially in ionic compounds, as we'll talk about, to achieve that. Any questions on that there? Now, we'll just touch upon it really quick, which is transition metals. They are really different and how they lose electrons. So if we took iron, which I believe is still 26, I hope, yes. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. We'll go with 3d6 there. That hopefully is 26, I hope. When iron, for example, which is a transition metal, loses 2 electrons, it will end up with 24 electrons. As we talked about just a second ago, there's actually a switch in terms of the energy of these orbitals when we start filling in the d orbitals with electrons. And what that means is it's actually always the s electrons that get lost first when you're dealing with a transition metal. So they will lose those 2 electrons there. And iron with a +2 charge will end up with 1s2, 2s2, 2p6, 3s2, 3p6, 3d6 as the proper electron configuration, or if you wanted to kind of shorthand it, argon 3d6. Now, an unusual sort of thing about transition metals are they actually don't end up back at noble gas configuration. And that is because they also have d electrons that they could dip into. So when iron makes a +3 charge, it has 23 electrons, which means the first ones that will be lost again are these 2 that are here in the s, but we actually need to lose 3 electrons. So once we get rid of the 2 electrons in the s, the next available electron is actually in the d, is where it will come out next. And you will end up with 1s2, 2s2, 2p6, 3s2, 3p6, 3d5 are argon 3d5. So transition metals, and only speaking of transition metals, they will always lose the s electrons first, then they will go into the d. And they again will usually never get back to a noble gas configuration because they would have to lose a lot of electrons to kind of get themselves back there. But they always kind of do that. So they're slightly different in what happens with transition metals. They typically will lose those S's first, and then if necessary, they will go into the D ones. Now, representative elements, which are basically our groups 1, 2, 3, when they lose electrons, they always back up to noble gases. And our non-metals, when they gain electrons in groups like 4, or really 3 through 8 there, they will gain electrons and go forward to a noble gas. So those guys on the end of the periodic table, they always back up to a noble gas, go forward to a noble gas. Those guys in transition metal really don't end up in that location. Any questions on that? Now, by the way, when we talk about something like calcium backing up to argon's configuration, just so we're clear, it is not becoming argon. It's just becoming like argon in terms of its electrons. The only way it could become argon would be to change the protons, right? And then it would no longer obviously be calcium. So we're just talking about changing electrons, which means in terms of electrons, it becomes very similar to a noble gas, but it's obviously still calcium in that sense because the protons have not changed. Question on electron configuration, how to write it, all that good stuff. Okay. All right, so let's talk a little about some periodic trends here to end this chapter. First off, valence electrons. Valence electrons are the outermost electrons. They are really important in terms of bonding. They're really the ones that are involved in bonding. And you can determine the valence electrons from the actual configuration, like we got there, nitrogen, which is 1s2, 2s2, 3p3, actually 2p, come here. Bad day writing numbers. All right, so 1s2, 2s2, 2p3. Remember that these first numbers here do represent the energy levels. So when we look at it, it is really these 5 electrons here, which are on the second energy level. That is the valence electrons. The electrons that are not the valence electrons and are lower in energy, closer to the nucleus, they are what are referred to as core electrons. So core electrons are those guys not involved in bonding, closer to the nucleus. Valence electrons are the one that are involved in bonding, and again are really your highest energy level electrons. They're really involved in bonding, as we'll talk about, because they're really not held as tightly, so they're easier to remove. They're also furthest away. So when two atoms come together, they are the first electrons that say hello to each other and sort of participate in bonding. Now, you could definitely write the electron configuration for everything to figure out the number of valence electrons, but there is a much easier way to do that. The group number on the periodic table equals the number of valence electrons. So everybody in group 1 has 1 valence electron. Everybody in group 2 has 2. Group 3, where aluminum is and all that, is 3. And then obviously 4, 5, 6, 7, and 8 valence electrons in group 8. The one exception for group 8 is helium. It only has 2 total electrons, so it only has 2 valence electrons. But everybody else in group 8 will have 8 valence electrons. Much easier way to do that. Again, we looked at chlorine a second ago, which was 1s2, 2s2, 2p6, 3s2, 3p. Come here. There we go. 3p5, and again, it is these guys here, which are the 7 valence electrons in chlorine. These guys would be our core electrons, and again, all you have to do is go chlorine's group 7, so it has 7 valence electrons. Much easier to figure it out. Carbon, which is group 4, has 4 valence electrons. Again, you could write out the configuration and determine it, or just go by group number. Let's talk a little bit about reactivity and metals and nonmetals. As you go down a group in terms of reactivity, for metals, you typically will see an increase in reactivity. And as we'll talk about, basically because they are larger, the electrons are further away from the nucleus, which means they are not held as tightly. They're good to go in terms of reacting in terms of that. Upper right of the periodic table is where we find the most reactive nonmetal for kind of opposite reasons. They are the smallest, which means they're ready to grab electrons up here, and they're the most reactive. So most reactive nonmetal up that way, most reactive metal on the periodic table found there. And the reason for that, we're going to talk about some periodic trends as to why that happens. So let's talk about that. First major trend and reason why we sort of see that is what is referred to as ionization energy. Ionization energy is the energy that's required to remove an electron from the gas phase in an atom. And if we have something that has very high ionization energy, it takes a lot of energy to remove an electron. If something has low ionization energy, it doesn't take as much to remove it. By the way, electrons do come off one at a time, and this shows that this is a metal that loses an electron, so it's on the right-hand side of the arrow like it's being given off. Electrons, like I said, really do come off one at a time. So for example, if you have something like magnesium, which is 12, the first thing that would happen is magnesium would lose 1 electron. And then that magnesium with a +1 charge would then lose another electron. And then that magnesium perhaps with a +2 charge would lose another electron. And every time an electron pops off, there's what is referred to as an ionization energy required to do that. This would be the first ionization energy. This would be the second ionization energy. And this would be the third ionization energy. Is it easier to remove the first electron or the second electron? Which one's easier? It is much easier to remove the first electron. What happens to the overall size of an atom when you lose an electron? Does it get bigger or smaller? It gets smaller. Electron cloud shrinks, right? Now those outer electrons have now just moved closer to the nucleus, right? Closer to that positive charge, which means your second electron and so forth are now going to be held a lot tighter. So we do see a lot more energy required as we go from the first to the second, and obviously second to the third. Now we see actually a really big jump in the case of magnesium as we go from second to third, because if we look at the electron configuration, 1s2, 2s2, 2p6, 3s2. Magnesium has how many valence electrons? It is group number 2, which means it has 2, and it would be these guys right here. Right, these are its valence electrons. These are the core electrons. So not a big deal when we pop off that first electron. We're still in the valence area. Gets a little bit harder to pop off that second electron. Now between the second and the third electron, we're now moving from valence electrons to core electrons. These guys started out closer to the nucleus to begin with, and they're finding themselves even more closer to the nucleus, right, as we keep removing electrons. And typically speaking, does not happen for something like magnesium, because it takes like maybe 10-fold the amount of energy going from the second to the third electron, and it just really doesn't happen under normal conditions. So popping off valence electrons are much easier. It does increase the energy as you go from one electron to the next, but once you go from valence electron to those core electrons, it is virtually impossible in normal conditions to pop off another electron, because it takes just so much energy, because really at that point, all the electrons have now moved very close to the nucleus. They're feeling a very strong positive charge. By the way, as we lose electrons, we now become a lot more protons than electrons, right? So bigger positive charge, like a bigger magnet to kind of bring those electrons in, and it holds them a lot tighter. So that's why there are certain things that will only make certain types of charges. Magnesium is an example of that. No matter what the situation, it's only +2 is the only thing it will make. And part of that reason is the ionization energy. Any questions on that? In general, when we look at the ionization energy, or the first ionization energy, which is that energy to remove an electron, it increases as you go up and to the right on the periodic table, decreases as you go left and down on the periodic table is the general trend. The other kind of important thing, or one important thing, is atomic size. It gets smaller as you go up and to the right on the periodic table. The size gets larger as you go left and down on the periodic table. Also, as you go to the right on the periodic table here, the much more protons, bigger positive charge happening, and helps everything. Even those outer electrons, because of that larger positive charge, are going to be brought in closer, making the overall size of the atom much smaller as you go up and to the right. Vice versa, as you go left and down, you have a lot more electrons, which are much, much higher energy levels and further away. So even though they're further away, they're not going to feel as much of a pull in. We get an overall bigger size going left and down. Now, some other important trends is what is known as electron affinity. Electron affinity is the energy change when an atom gains an electron. And it also increases as you go up and to the right on the periodic table, decreases as you go down on the periodic table and to the left. Another important, by the way, when somebody gains an electron, becomes negatively charged, which is what we're talking about here. The size of the negative ion, is it larger or smaller than the neutral guy? If somebody gains an electron, it becomes larger. It gains an electron to its electron field or electron cloud, the whole thing gets larger. So a negative ion is larger than the neutral guy. A positive ion is actually smaller than the neutral guy because it loses its electron field or cloud. One last sort of trend that's really important is electronegativity, which we'll talk about in bonding as well. And that is the ability of an atom to bring electrons towards itself. And that also increases as you go right and up, with fluorine being the most electronegative, and decreases as you go down. So if we kind of put together all of our trends, it really helps us understand what happens with nonmetals versus metals. When we look at the periodic table and we go up and to the right on the periodic table, we have, we'll just write in here, we have the atomic size gets smaller. We have the ionization energy increases, decreases this way. We have the electron affinity increase as you go this way and decrease as you go down. And lastly, we have electronegativity, increase as you go this way and decrease as you go down. So basically, as we go up and to the right on the periodic table, we have things that are much smaller, which means even the outer electrons are held tighter to that nucleus, which means it takes a lot more energy to remove an electron. Not only that, they also would rather gain electrons and bring electrons towards themselves. And that's why what we think about with nonmetals, they are typically the guys that want to gain electrons because of all those trends. Everybody's smaller, they will hold on to their electrons, and not only will they hold on to their electrons, they will see your electrons and go, I would like your electrons as well. So they want to bring electrons towards themselves. When we think about metals on the other side, as we go left and down on the periodic table, we have atoms which are larger, which means the outer electrons are further away from the nucleus. They're not held as tightly, which means it doesn't take a lot of ionization energy to remove an electron. They have very low electron affinity and very low electronegativity, which both of those mean they don't want your electrons. They don't really want to hold on to their electrons. They would much rather give away their electrons. And that is why we see metals typically are the ones that will lose electrons and become positively charged. Why again, our nonmetals will become negatively charged as they gain electrons. Any questions on any of that there? So these sort of periodic trends also help us understand when we talk about bonding, some of the different types of bonding that we will get into, why in certain cases we actually do see a transfer of electrons from one element to the next, especially when we have a metal and non-metal come together, we get that complete transfer of electrons. Also why when we put two nonmetals together, they're all hanging out at the same spot on the periodic table, which means they both don't want to give up their electrons. So what we end up seeing when two nonmetals come together in terms of bonding is they actually will share electrons rather than a transfer of electron because of these periodic trends. Any questions on any of that there? All right. Let's talk a little about Lewis dot symbols. Lewis dot symbols are also sometimes called electron dot symbols. And basically, we use a dot to represent each of the valence electrons in an atom. It is only the valence electrons that are shown in these sort of structures, and that is because they are the only electrons that are involved in bonding. They obviously have a lot more. The number of valence electrons, as we just talked about, does equal the group number. So if we were to write the Lewis dot symbol or electron dot symbol for sodium, it basically would have one dot to represent the one valence electron. If we were doing calcium, it would have a couple of dots. That's an A. Basically, we use the symbol, and there's really no rule other than no more than really 2 dots per side. Yeah, so no more than 2 dots per side is typically the rule there. Most people kind of go around one at a time and repair them, but it doesn't really matter as long as you don't go over 2 per side. 2 per side on the 4 side gives you how many electrons? 8 is a magical number when we talk about bonding. 8 gets us to noble gases, which again, as we talked about a second ago, is really the basis of bonding. So, you know, that's typically what we're trying to achieve here. So I think, there you go. So here's again some Lewis dot symbols or electron dot symbols. Again, everybody in group 1 has 1. Everybody in group 2 has 2, 3, 4, 5, 6, 7, 8. Again, this one exception, as I talked about earlier, it is helium. It only has a maximum of 2 electrons total. So they are both the valence electrons in this particular case. We don't have to worry too much about valence electrons or dot symbols for transition metals, so you don't have to worry about it. But just our representative elements are the ones that we typically come across. Any questions on that there? All right, that should wrap up, I believe. That should wrap up this chapter, if I'm not mistaken. So give me a yes. Yeah. About the, say one more. Okay, yeah. Yeah, there's really no fast rule unless you find something that's super picky. The only real rule is not to go more than 2 per side. So again, a lot of times people will, and I might not have done it on here when I was making it, but sometimes people will just kind of go one per side and then kind of pair them back up. And that's fine. But really, the only rule I've ever seen, is really just not more than 2 per side. That's it. Yep. Chem is a week. Next week, I think we will do it on Wednesday. And it will cover, I believe, chapters 1 through 4. All right. So this will not be obviously on next week's exam. We're going to talk about naming in here. We're going to talk about bonding as well. We are skipping chapter 5 in our book, which I believe is nuclear chemistry. So we're not going to do chapter 5, which I think should be nuclear chemistry. So we're just skipping it altogether. All right. Any questions on that there? Okay. So we're going to really talk about nomenclature here first, which is naming. And a couple of things. First off, we talked about things making charges, but just to make sure everybody's on the same page, there are certain things on the periodic table that will always make sort of a fixed charge. So everybody in group 1 will always make a +1 charge. So things like lithium, sodium, and those guys, potassium. Everybody in group 2, like our calcium or barium and those guys, will make +2. Then we kind of have our transition metals here, which they can make a varied charge. So they can have a variable charge or varied charge. Then we go to group 3, and we got sort of that staircase coming down right around group 3. And usually here in aluminum is what we're talking about. Aluminum can be a +3. Then we go to group 4, 5, 6, 7, and 8. And when we go to group 4, there's really no good pattern because of the staircase there. You got nonmetals up on top, you got metalloids, and you got actually metals below the staircase there. But going to group number 5 in our nonmetals, they will make a -3 charge. Group 6 will make a -2 charge, and group 7 will make a -1 charge. And again, we're talking about our nonmetals here above the staircase that we're talking about. Now, in terms of our transition metals, as I talked about, they could have a variable type of charge. There are, though, 3 exceptions to that. There is zinc and cadmium, which when they do form a charge will always form +2. Then if you hang a left there by cadmium, that is silver, and it will always be a +1 charge. Other than that, most everybody else in the transition metal region can make multiple types of charges. So everybody over here, everybody sort of in this region, multiple charges, and also down in this region where we see things like lead, antimony, tin, those guys also are metals below the staircase. They can have a variety of charges depending on the situation. So for example, something like copper, which we talked about a little bit earlier, could be +1 in certain situations. It could also be +2 in other situations. Something like sodium will always be +1, no matter what the situation is. It will never be anything other than that. So these guys here that have the fixed charges, 100% of the time, always going to be those charges, again, no matter what the situation may be. Any questions on that there? All right, so we're going to talk about some common names, and there's a few things that no matter what the situation is, we really do go by sort of common names. H2O is a big one. H2O is water. It is not dihydrogen monoxide because nobody wants a refreshing glass of dihydrogen monoxide, right? Or anything like that. Probably why they don't call it that, I suppose. So when you do see H2O, it's not a trick question. It is water. NH3 is ammonia. That's also something that comes out a lot. CH4 is methane. I'd say not to worry too much about the last two. Most people will actually call it sodium chloride rather than table salt. And most people will call it, sucrose or something like that. But definitely these first 3 here, if you come across any of these first 3, those are the names that you definitely should use, regardless of the sort of correct way of naming things. Again, H2O, water, ammonia, NH3, and methane, CH4. Now, we're going to talk about really two types of compounds here. And one is an ionic compound. And the way we name ionic compounds are a little bit different than the way we name molecular compounds or covalent compounds. Ionic compounds is the first one here. It always contains a metal and a non-metal. So when we're naming an ionic compound, it's a metal and non-metal. And basically what's happening is, as we sort of talked about a second ago, the metal is going to give up an electron to the non-metal. At that point, the metal will then become positively charged, or a cation. The non-metal will then pick up the electron or two, or however many. It will then become negatively charged, or an anion. And what holds that together, an ionic compound or an ionic bond, is simply that attraction between the positive and negative guy. There's absolutely no sharing of electrons there. It is what is referred to as electrostatic attraction. The other type of naming we're going to talk about will contain two nonmetals. These are sometimes referred to as molecular compounds or covalent compounds. And in this case, because of those periodic trends we just talked about, everybody's up in the right-hand side of the periodic table, which means they share very similar trends in terms of, I want to keep my electron, you want to keep your electron. So what ends up happening is we actually get the best that we could do is actually sharing of electrons. So neither one of them want to give away their electrons like a metal. So because they're both nonmetals, what ends up happening is they agree upon, we'll share the electrons. How about that? And as we will talk about, the sharing may be equal, the sharing may be unequal, but there's some aspect of sharing that occurs always when you put together two nonmetals, and that's really what holds that together. And a metal and a nonmetal, there's absolutely no sharing of electrons, a complete transfer of electrons from one to the next. And really where we form ionic compounds and ions from is in that process. So let's talk about naming these guys and the proper way to do it. A binary ionic compound contains a cation and an anion, a positive and negative ion. When we write the formula, a couple important things. First off, it is always the positive guy first, followed by the negative. So it should always be the cation followed by the anion. When we put together in a formula something that's positive and negatively charged, we should always end up with an overall charge of 0. And what that means is, for example, if I take a sodium ion and a chloride ion, I want to put them together, that is +1 and -1, which means I just need one of each. And I end up with a sodium chloride formula. The sodium chloride formula does not have any overall charge, but it is actually made up of two ions, a sodium ion that has a +1 charge and a chloride ion that has a -1 charge, and they are balanced together. That is also why if I put together my sodium ion and an oxygen or oxide ion, this is +1 and -2. If I just put those together just like that, I'm going to end up with an overall charge of -1, right? +1 -2 gives me a -1. To counteract that and to do it properly, I need one more sodium ion. +1 and +1 gives me a grand total of +2 to match the -2. And when I would put it together to write the proper formula, it should look like that. Again, no charges written in the formula for an ionic compound, but it actually is made up of two things that have charges. It's made up of two sodium ions that have a +1 charge and one oxide ion that has a -2 charge. Any questions on that there? So that's a really important thing to sort of keep in mind when you put them together in an actual formula. The formula for the ionic compound should have no charge, but it is actually made up of things that do have charges, and you want to make sure you get to 0 in terms of the overall charge to balance it out. Sometimes you need more of the positive guys, sometimes you need more of the negative guys, sometimes you need more of both of them to get you there to 0. So let's talk a little bit about, first off, how we name some of these ions before we get into that. Let's go back here real quick. So when we have ions that are cations, and these are our positive ions, if we just had the ion by itself, we can name it simply by using the whole name of the element. So if we had the H plus ion, that would be the hydrogen ion. If we had the Li plus, it would be the lithium ion. We had the Ca2 plus, it would be the calcium ion. So the way that we name anybody that is a positive ion is simply, we just use the whole name. And if it is just the ion by itself, when you write the formula, you should have the charge like we have here. And you just basically put ion at the end of it. Now, anions, which come from nonmetals, are a little bit different in terms of how we name those guys. We actually use the root of the name, and then we kind of change the last part to IDE. So they get the IDE part of it. So O2 minus, which is oxygen, oxygen becomes the oxide ion, IDE. Br minus, bromide becomes the, bromine becomes the bromide, IDE ion. If we had N3 minus, nitrogen becomes the nitride, IDE ion. And hydrogen has some of those unusual properties. It's one of the only elements that could go both ways. In certain cases, it is positive. In most cases, it could actually go negative as well. And it's named the same way. It becomes the hydride, IDE ion in this particular case. So if you just have the ions by itself and you want to write the formula for an ion by itself, it should have a charge because it's an ion. And if it is a positive ion, you just use the whole name of the element. If it is a negative ion, you drop the last part of the name and put IDE at the end of it. And it is something with a negative charge. Question on that there. Okay. So let's talk a little bit about type 1 and type 2 compounds that they're sometimes referred to. Type 1 and type 2 compounds, these are both ionic compounds, which means what we are dealing with here is a metal and a non-metal. And whenever you have a metal and a non-metal together, the one that is the most important is always the metal. It is always the most important one in terms of how you properly name it. A type 1 compound is when we have a metal that has a fixed positive charge. So those are our guys in group 1, 2, 3. That is zinc, cadmium, and silver. These are all what are referred to as type 1 metals, which means no matter what the situation, always going to be basically the same positive charge that's there. Now, type 2 compounds, as we'll talk about, are pretty much everybody else. So that is pretty much when the metal is a transition metal. Are just to the right below the staircase. And what I mean by that, if you look at the periodic table, again, our staircase comes down. That is the transition metal. There's these metals down here below the staircase. Things like lead, as I wrote before, tin, antimony, bismuth. These guys, which technically are not transition metals, but they're just to the right on the periodic table. They behave like transition metals. They could have a variety of charges. And something like chromium, for example, in certain cases could be chromium with a +2 charge, could be chromium with a +3 charge. Copper, for example, can be +1 or +2. So depending on the metal, there are different ways that we name ionic compounds when we come across them. And type 1 and type 2 are always ionic, and metal, non-metal. And it's always the metal, basically, that you want to look at. Any questions on that so far? Okay. So here are those ions as we talked about. Again, guys on the left there are positive. Whole name of the metal, IDE for everybody there on the right. So let's talk about the rules for naming type 1 compounds. It's pretty straightforward. If you have a type 1 compound, it is always going to again be the positive guy followed by the negative guy, which means you're going to take the whole name of the metal. And for your non-metal, you're just going to drop the last part and put IDE, and you will have your name. So for example, when we look at NaCl, sodium is a metal, Cl is a non-metal. All I need to do is look at this guy and I see sodium. I go to the periodic table, I see it is group 1, which means it's a type 1 metal, which means I don't need to look any further at this point. All I need to do is use the whole name for the metal, which would be sodium. And the chlorine becomes chloride, IDE at the end of it. I take a look at CaBr2. I look at this one, which is Ca, which is calcium, which is a metal. I look at this guy, which is bromine, which is a nonmetal. That first tells me it's an ionic compound. The important part here is the calcium. Calcium is which group? It is group 2 on the periodic table, which means it has a fixed charge, which means the name of this guy should be whole name of the metal, which would be calcium. And the nonmetal gets the IDE, which would be bromide, IDE. So this is calcium bromide. Now, a very common mistake that people make or concern that people have is, what about the 2? I feel like I should say dibromide because it just sounds better. It doesn't sound better in this case. It sounds wrong in this case. Don't do that. So the 2 here has no effect on the name. In an ionic compound, you could have 42 there on the bottom. You probably won't, but you could have 42 of those guys. You would still just call it bromide. Doesn't matter how many metals you have in an ionic compound. You just use the whole name. And it doesn't matter how many non-metals you have. It just means that you call it bromide in this particular case. Do not use prefixes like di and stuff in the ionic compound. It will be wrong. Why is the 2 there? The 2 is there for what reason? To make it equal 0, right? Because calcium is group number 2, which means it has a +2 charge. Bromine is group 7, which means it has a -1 charge. Again, to get us to 0, we actually need 2 of those, right? It gives us a -2 to balance out the +2 on the calcium. And that is why the 2 is there, but has absolutely no effect on the actual name. Any questions on that there? Now, when we talk about writing formulas, as we talked about earlier, although when we do put a positive and negative together, we end up with no charge, we should always keep in mind it is really 2 things that do have charges, but you should never have a charge in an ionic actual compound there in terms of the formula. So when we look at this guy, which is K, which is potassium, which is a metal, I is iodine, which is a non-metal. Again, the metal important, potassium is group 1, tells us it's type 1. We proceed with the whole name of the metal, which is potassium. And again, we give the IDE there to the non-metal, which is iodide. And this would be potassium iodide, really made up of a cation that is K+, and an anion that is I-. And that is why the formula is Ki, because we just need one of each of those to get us to 0. Any questions on that there? Okay. So let's take a look at some examples and see how you do here, perhaps. There we go. So we kind of jumped the gun on that. So we'll change this one. Why don't we do BaCl2? And while you're at it, why don't you also try to write the formulas for, let us do calcium nitride. Let's do aluminum oxide. And why don't you try to write the formula 4. Let's do sodium. Let's do sodium something. Let's do sodium sulfide. All right, so let's go names on these guys, correct formulas on those guys. Take a couple minutes, see what you come up with. So again, first thing you want to do is identify what you're dealing with. So K is potassium, which is a metal. Cl is chlorine, which is a non-metal. First off, that tells you it's an ionic compound. Always in this situation, you want to look at the metal. The metal, which is potassium, is group number 1, tells you it has a fixed charge. It tells you it's a type 1 compound, which means you're pretty much done. You just need to use the whole name of the metal, which is potassium, and give the non-metal the IDE at the end of it, and it would be potassium chloride. Again, the cation here would be K+. The anion would be -1 there for the chloride, which is why when we put it together, we just need one of each to give us the KCl. Any questions on that one? Same sort of approach here. Looking here, this is barium, which is a metal. Cl, again, a non-metal in this case, telling you it's an ionic compound. We want to focus our attention here on the barium. That is group number 2, which tells you it has a fixed charge of +2. And that means that that's all we need to worry about here. So this is going to be barium. And again, that 2 has no effect on the name. So it will be barium chloride in this case. Again, the 2 is there because the barium does have a +2 charge. Each chloride is -1. So to balance it out, we need not 1, but again, we need 2 of them there to balance out the formula, but has no effect on the name. Any questions on that there? Lastly, here we look at barium, which is a metal. We look at hydrogen, which is a non-metal, right? Remember that? So hydrogen actually is a non-metal. Here we're looking at barium, just like we did before, has a fixed charge. So this would be barium, and hydrogen is actually negative here. Would become hydride. Again, the 2 here would have no effect on the name. This is a barium with a +2 charge. And whenever hydrogen comes second in the formula after a metal, it is actually -1 in this particular case. And that is, again, why we have 2 of them there to balance out the charge that we see on the barium. Otherwise, if hydrogen in most cases is positive, this is the one case where it will be negative if you have it after a metal in a formula. If you don't have it after a metal, then it's positive, but before that, it would be negative if it comes after a metal. Any questions on those? All right, so we want to write the proper formulas here. So this is really going to be based off of the name and writing the right ions. So first off, we see calcium nitride. Calcium is group 2, which means it should have a +2 charge. Nitride is nitrogen from the periodic table, which is group number 5, which means it should actually have a -3 charge. Again, we want to put this together to equal 0. The easiest way to do that is common number between 3 and 2 is 6. Yes, you just multiply the 2 numbers together, it gets you 6. In order to get calcium to 6, I don't need 1. I don't need 2, but I do need 3. To get the nitride to 6, I need 2, and that gives us our proper formula here. Ca3N2. Bad day with numbers. There we go. So Ca3N2 would be our proper one. By the way, sometimes people teach you to do this move that way and that way with the charge. It works in like 90% of the time. It doesn't work 100% of the time. So you should keep that in mind. If you just blindly kind of move the charges down in the opposite locations or go the opposite way, it works more times than not, but there's a lot of cases where it will not work correctly. So it's best to keep in mind that your goal is to get to 0 in terms of the charge. And again, sometimes people will say you could just do this move. Again, works about 90-ish% of the time, not 100% of the time. So don't just blindly kind of move the charges. Think about getting it to 0. Any questions on that one there? We'll do the same thing here with aluminum, which is group 3. So that's a +3. Our oxygen is group 6, which is a -2. Same deal here. this is going to get us to 6 is what we need. To get our aluminum to 6, we need 2 of them. To get our oxygen to 6, we need 3 of them, right? Again, we write them all out and just add up the charges. That is basically what you're going on there. +6 and -6 will equal 0. Questions on that one there? Lastly, sodium, which is group 1, which is a +1. Sulfide is sulfur, which is group 6, I believe still. And that is a -2. In this case, we actually need another sodium there to balance out the charge to get us the +2 and -2. That means the proper formula here, Na2S, would be it. So get out of the way. Na2S. Any questions on that there? So these are all type 1 guys. These all have fixed charges. Again, it's always the metal, which is the most important that you want to look at. And pretty much at that point, you can just roll with the name as soon as you identify as a type 1, whole name of the metal, IDE on the non-metal, regardless of how many you have of either one of those. It does not make a difference. Any questions on type 1 compounds? Okay. Now let's talk about type 2 compounds. Type 2 compounds pretty much are identical to type 1. The difference is, again, the metal, which is important. So type 2, again, we're talking about a metal and a non-metal. The metal is the important one here. It is a transition metal, or to the right of those. And these basically have a very positive charge. So if we look at something like FeCl2, the first thing we would want to look at is we would want to look at that iron is a metal, Cl is a non-metal. So again, we're dealing with an ionic compound. We want to locate iron, and you can find iron right there in the transition metal region at number 26, dead center. That automatically should pretty much tell you this is a type 2 compound. So if you look at the metal, you see it's in the transition metal region just to the right where there's lead, tin below the staircase. Those are all guys that have a variable charge. So what that means is you got to do a little bit of work here. Perhaps you want to take the iron and go, well, maybe I don't know what the charge is at this point, because it could be +2, +3, whatever it may be. The good news is you will always know the charge of what it's attached to. So in this case, we know that Cl is group number 7, which means it should have a -1 charge. There's not just one Cl there, but there are 2, which means the overall negative charge is -2. Remember that we need to balance out to 0. That means that the charge on the iron is +2 to balance it out. So you're going to have to work your way backwards, and you'll always know what the negative guy's charge is. You need to figure out what the positive guy's charge is to get yourself to 0. The good news is we name it the exact same way. We take the whole name of the metal. We still do the non-metal with the IDE. The difference is here we use Roman numerals. And what does the Roman numeral indicate? The Roman numeral indicates the charge on the metal is what the Roman numeral indicates. Is what the Roman numeral indicates. It does not indicate how many you have, which is a very common mistake people make. It indicates if you took out one of the metal ions that are positive by themselves, what the positive charge is. So we would use still the whole name of the metal in this case, which would be iron. The charge on that iron is Roman numeral 2. And the Cl becomes chloride here. Again, no dichloride, just chloride, just like previous. And this would be known as iron Roman numeral 2 chloride. So it's named very similar to how we name type 1. The difference is we need to figure out what the charge is on the positive guy. and we need to insert basically a Roman numeral to indicate the positive charge. Other than that, just like before, you could have 42 chlorides there at the end. It would just be called chloride, no prefixes, just Roman numerals in this particular case. This goes for pretty much all transition metals, except for the 3 we talked about that have fixed charges: zinc, cadmium, and silver. Those are really type 1 compounds or metals because they have fixed charges. But every other transition metal is a key. You should be doing this. Anything that is to the right of the transition metals where lead is, you should also be doing it as well. Any questions on that? So why don't you take a second and see what the name of this guy would be. PB is lead. It is just to the right of transition metals, but that is the area I've been talking about that is named the same way. Oxygen, which is a non-metal, automatically tells us it's ionic compound. We want to look at the lead. Again, it's not really a transition metal, but just to the right. So they are treated the same way. But that automatically tells us we were dealing with a type 2. That also tells us that I'm not really sure what the lead charge is, but looking at the oxygen, I should know it is group number 2, which means group number 6, which means it has a -2 charge. And there's not one of them, but there are 2 of them, which means our overall negative charge here is -4. In this particular case, our lead actually is +4. And the correct name here would be lead 4 oxide in this particular case. First off, any question on that name? This is an example where if you tried the crossover move here, you would get it wrong. Yes, you would move the 2 over and the 1 over, and both of those things would be incorrect. So again, it's best to think about it, getting yourself to 0. And if it helps you, just draw it out like that and count up the charges. Yeah, it's an easy visual way to figure out, what charges are going to be. Any questions on that one there? Okay. Now, there is sort of an older way of naming, which we're really not going to use here, but kind of root names and stuff like that where they don't use Roman numerals, but you'll sometimes still see names like ferric chloride, which is iron 3 chloride, ferrous chloride, which is iron 2 chloride. So they'll sometimes use some older names. We will not use any of these older names which end in ic or us. We will strictly use Roman numerals to name these type of compounds, but occasionally you still sort of see it pop up occasionally along the way. And that's what this table shows you, sort of, no, it doesn't. Shows you the Roman numerals there, and our type 2 compounds. All right, so as we talked about, pretty straightforward. You want to use the whole name of the metal, IDE for our non-metal. And again, the only additional thing we're going to put into type 2 is our Roman numeral. So let's take a look at some here to finish it out here for today. So for each of these, give the proper name and then also give the formula for some of these here. Let's do so give the proper formula for nickel 4 bromide. Let's do copper 2 oxide. And let's do lead 4 sulfide. All right, names on the left, formulas on the right. We have CO, which is a metal, our Cl, which is a non-metal. We want to look at the CO and we find it in the transition metal region. That should automatically tell us it's type 2. That means may not know what the charge is on the cobalt, but I do know that Cl is -1 and there are 3 of them, which means that my cobalt here does need to be +3 to balance it out. This would give me a name of cobalt Roman numeral 3 because of the charge, not how many we have. And again, 3 chlorides doesn't matter for the name. This would just be chloride in this case. So cobalt Roman numeral 3 chloride. Any questions on that one there? Same thing here. We see Cu, which is copper, I, which is iodine, metal, non-metal, copper transition metal tells us again we should figure out the charge is type 2. Our iodide is group 7, which is -1. So in this particular case, the copper does have to be +1 to balance it out. Whole name of the metal, which would be copper, Roman numeral 1 because of the charge, and the iodide becomes iodide, IDE at the end of it, copper 1 iodide. Any questions on that one there? Sn is tin, which is a metal. Br is bromine, which is a non-metal. Tin is not technically a transition metal, but it is one of those guys to the right underneath the staircase by lead. So we will treat it the same way. So we're not sure what the charge is, but we do know that Br is -1. And again, there are 4 of them, which gives us a -4. That means that our tin here has to be +4. And that would get us tin Roman numeral 4 because of the charge. And even though there's 4 of them, just going to call it bromide at the end. Any question on any of those names? All right, so let's just do a couple of these here before we call it. When we have the name and want to go backwards, we do get a lot of information here. Nickel Roman numeral 4 should tell us I have a nickel with what type of charge? +4. You don't have to figure it out. It actually tells you, right? So that is the charge. Bromide, which is bromine, which is group 7, which is a -1 charge. To put these together, we need more of the Br, right? We need a grand total of 4 to balance it out, would give us NiBr4 as our proper formula there. Question on that one? Copper Roman numeral 2 tells us the copper has what type of charge? +2. Oxide is oxygen, which is group 6, which means it has a -2. In this case, we just need 1 of each, right? So CuO will do us. +2 -2 equals 0 when you put it together. Lastly, lead Roman numeral 4 will again tell us that the lead has a +4 charge because of that. Sulfide is sulfur on the periodic table, which is group 6, which has a -2 charge. In this case, we need more of the sulfide, right? We need a grand total of 2 of them. Gives us a PbS2 for our formula there. Question on type 2, very similar to type 1. Additional thing on the naming part is the Roman numeral, and it is the charge on each individual metal ion. Any questions on any of that there? All right, we will lay it